Welcome to this explainer. Today, we're tackling a massive, literally deep water problem. How a floating drill ship figures out its exact location in the middle of a restless ocean so it can actually command its 6 thrusters. It's an absolutely fascinating challenge of engineering and physics, and I am super excited to break it down for you. Section 1. The station-keeping problem, battling the ocean. Picture this totally chaotic environment. We're talking 56 km/h winds and relentless, heavy seas constantly slamming the vessel broadside. But despite all those crazy forces, the dynamic positioning system, or DP system, has to hold the ship safely within just 1 single meter of its set point, directly over the wellhead. I mean, think about that margin of error for a second. 1 meter, in the middle of the open ocean. It's absolutely wild. So if you were to walk right up onto the bridge and ask a DP operator, hey, where are we? You'd probably expect them to just rattle off some GPS coordinates, right? Well, you'd actually get a really counterintuitive answer. They'd look at you and honestly say, nowhere, until at least 3 independent systems agree. And honestly, this brilliantly illustrates the absolute core rule of DP Class 3 operations. The computer never, ever inherently trusts a single sensor. It completely demands a consensus. Moving on to Section 2, meet the 4 witnesses, the sensor suite. Let's meet the 4 unique technologies that are constantly testifying to the ship's actual location and the environmental loads pushing against it. On a modern vessel like the GF-12000, we're talking about differential GPS, which uses spot beam demodulators, and HIPAP, which is hydroacoustic positioning. Then we have our 3-axis motion reference units, or MRUs, actually feeling the tilt and heave of the ship, and finally, ultrasonic wind sensors that measure the weather forces before they even have a chance to physically move the vessel. Now, what's really fascinating here is the sheer contrast in how these systems gather their data. DGPS looks straight up at space to refine satellite signals. Meanwhile, HIPAP looks in the exact opposite direction. It looks straight down into the pitch-black water, pinging acoustic transponders sitting all the way down on the seabed. Which brings us to Section 3, how sonar finds the bottom. HIPAP ranging. In plain English, HIPAP is essentially a highly advanced sonar for the drill ship. It sends a sound pulse down to a beacon on the seabed, and then it times exactly how long it takes for that returning echo to bounce back up to the ship's hull. So the crucial step here is converting that tiny, tiny fraction of a second of signal travel time into a precise physical distance in meters. To do this, the system uses a mathematical formula where it simply multiplies the speed of sound in water by the time it took the signal to travel. But wait a second, why do we divide by 2 at the end of that formula? Well, it's kind of a fun little logic puzzle. The sound pulse has to travel down to the bottom, and the echo has to travel back up. We divide by 2 because we only want the distance to the bottom, not the whole round trip. Unless, the ship somehow plans on drilling into itself, which is definitely a bad idea. All right, Section 4, the DP voting algorithm, the skeptical jury. With all this data pouring in, the DP computer acts exactly like a highly skeptical jury weighing witness testimony. Using some incredibly complex math known as Kalman filtering, the voting algorithm cross-checks all of these references simultaneously, every fraction of a second. It doesn't take anyone's testimony at face value. It is deliberately searching for disagreement to root out bad data. Let's put this into a real-world scenario. Imagine one witness, say one of our dual HIPAP units, suddenly claims you are 15 meters away from what the DGPS and the other HIPAP unit are saying. What happens then? Well, the jury doesn't just blindly average the numbers together. If you averaged a 15-meter error into your position fix, you'd be pulled right off the wellhead. No way. Instead, the system automatically recognizes the outlier, basically the liar in the room, and completely discards its bad data to protect that strict 1-meter set point. Next up, Section 5, when the ocean lies, environmental disruptors. So you might be wondering what actually causes these highly advanced, multi-million-dollar sensors to lie to the computer in the first place. Well, every single technology has a weakness. For DGPS, satellite signals can actually drift off true position due to atmospheric effects. And for HIPAP, the failure mode often comes from thermocline layers in the water. Thermoclines are invisible ocean layers caused by temperature-driven density changes, and they act kind of like invisible funhouse mirrors, literally bending the acoustic sound waves as they pass through. This makes the seabed transponder appear to be in a completely different location. It's a really dangerous villain in our story here, and operators have to actively recognize this rather than just assuming the drifting numbers are normal system noise. Let's wrap up with Section 6. Disagreement is the goal, the ultimate safety net. This brings us to the ultimate philosophy behind this incredible piece of maritime engineering. The absolute crucial point to take away from this explainer can be summed up like this. The system is built on disagreement detection, not just accuracy. Like we've seen, no single position reference is ever inherently trusted alone. And this is exactly why we never, ever operate DP3 well operations with fewer than the minimum independent references active, which is usually 2 to 3. If you lose those backup references, you aren't just losing accuracy, you are literally blinding the jury. Because at the end of the day, accuracy is totally useless without disagreement detection. Knowing where you are is only useful if you can actually catch the lies. This strict requirement for independent systems ensures that a single drifting sensor won't accidentally drive the ship off position and cause a catastrophic disconnect of the rigid riser from the wellhead. It leaves us with a fascinating final thought. In the middle of a chaotic ocean with lives and subsea infrastructure on the line, the safest computer system is the one that constantly expects to be lied to. So I'll leave you with this. If your data sources never disagree, are you really operating in the real world? Thanks so much for joining me on this explainer.